Um, this is the tutorial, the replication crisis, tutorial, empirical science crisis, and the implications for human subject research and mixed reality. This will be taught by myself, Ed Swan, and Mohammed Safayet Arifan is right here. And we are both at Mississippi State University. I think to ask questions, you type it in this Twitch channel, and I can see the Twitch channel, and I can see your faces if you shared your video. And let's go. And let's see, my mouse in the right spot. So this is the outline of what I will talk about. The tutorial will be broken into two parts. The first part is what I'm about to start presenting right here. And the second part will be presented by Arifan. So I'm going to first talk about the replication crisis. And then the replication crisis is going to involve a particular paper that we will cover in some depth. And that paper, in order to deeply understand what's in it, going to review some aspects of inferential statistics. So we'll talk a little bit about hypothesis testing, and then power, effect size, and p-value. Having done that, we're going to cover the paper in some detail. It's called the Reproducibility Project Psychology. And then we're going to talk about what that means. And then we'll talk about what we should do for my talk. And one of the things that will come out of this part of the tutorial is a call for our community to be more accepting of replication studies. I think our community has become more accepting of replication studies over the past few years. I first gave the first part of this tutorial at VR 2018 in Reutlingen. And since then, there has been some change, but I'm going to make the case again here. After I finish talking, Arifan is going to present his own scholarship on the state of replication studies within our field. Okay. So let me figure out exactly where to click. There we go. No, why isn't it? Oh yeah. Okay, so this screen is here. Okay. So first, let's talk about the replication crisis. So what is the replication crisis? It's also called the reproducibility crisis. So a major goal of science is reproducibility. So if you run an experiment, the result should be reproducible for you the next time that experiment is run. And we want things to be reproducible in our lives. For example, your car worked yesterday, you expect it to work today, you expect it to work tomorrow. And without this expectation, many of the things that we do in the modern world would not be possible. A more compelling example maybe, and the reason why I'm presenting this from my office in my house and not in Portugal to you live, a drug has a certain effect in an experiment, and we expect the same effect if prescribed today. So when we get our COVID vaccine, we expect the effect to be as it was in the clinical trials where the drugs were rigorously tested. Within our field, and in particular within work that my lab has been performing, if a virtual object is perceived to be in a certain location in an experiment, we hope that object is perceived in the same location when anyone else looks at it. So there's been a series of alarmingly headlined studies. Oh, why did it do that? No. So if I don't click on the exact right thing, it kills the screen. Can you all still see the talk?
Yeah, I think we're seeing that.
Okay, good, good. Okay, so here's an example of a headline that has appeared in the last 10 years. So lies, damn lies, and medical science. Another one, unreliable research, trouble at the lab. In The Economist, this is a widely read economics magazine out of Britain. This is a pretty famous paper in the reproducibility literature by John Ioannidis. Why most published research findings are false. So that's not a very happy title. Come on, you can do it. And the replication crisis. Believe it or not, how much can we rely on published data on potential drug targets? From Salon, cancer research in crisis are the drugs we count on based on bad science. And then in my own scholarship in this area, this here was the most bleak and negative view that I found. Big science is broken. So these are just an example of headlines that have appeared within the past 10 years. So the problem has been the failure to replicate many published findings, even findings discussed in textbooks. And the source of the problem has been determined to be 3 different types of biases that occur in research. First is publication bias, where only significant results tend to be published. And we'll talk about how the culture of scientific endeavor leads to this bias. Selection bias, only significant results are typically selected for analysis. And finally, reporting bias, only significant results are reported. So publication bias, selection bias, reporting bias. Because of this, replication studies are rarely funded and are therefore rarely published, because if you can't get funding to do the work and you can't publish the work, why would you do the work? You know? And therefore, most studies in science are exploratory in nature and not confirmatory. So looking for new phenomena, new things, new findings. And we'll talk about the surprisingness bias as well in this talk. So this is the problem. If you were to read the headlines of the last slide, you know, this would be the problem that they discussed. So what is the evidence for this problem? So the problem became known in the popular press and began generating the headlines you saw based on something that occurred in the field of cancer biology. In 2011, there was an analysis performed, and a series of cancer drugs that had been developed over many years, many millions of dollars of R&D development, 95% of these drugs failed in some clinical trials. So how can medical science make progress against cancer if 95% of the drugs that make it to the clinical trial stage don't actually work? So this led to some replication studies in the 2011-2012 timeframe on drug effectiveness. And then in some other fields, including psychology, other replication studies followed. So this is what was found. So Bayer, the Bayer company, replicated a bunch of drug studies and found that only 21% successfully replicated. That is, whatever the claim was in the paper that drove the development of a drug, only 21% were able to be replicated. Amgen is another big drug company, found that 11% were replicated. The National Institute for Neurological Disorders and Stroke was only able to replicate 8% of its studies. The most alarming of all, the ALS Therapy Development Institute. ALS, known as Lou Gehrig's disease, is a terrible fate, and 0% replicated out of 47 studies. So how can medical science and us as a society make progress against an illness as terrible as ALS if none of the studies can be replicated? So this is all terrible news, but it's all in the medical domain. This, highlighted in red here, is the project that this tutorial is based on. So within psychology, there was a large effort called the Reproducibility Project, and this found that 36% of a series of psychological studies were able to be replicated. So this is the evidence for the replication crisis right here. Any questions or thoughts about this? I guess if I see a question, it will appear in this Discord window. Okay. And if I don't keep my mouse in the exact right area, it doesn't advance properly. So these studies were conducted in biomedicine and psychology. In addition, some surveys were performed at this time, which is about 7 years ago. And in these surveys, people were asked in a wide variety of fields. And I think some of us got this email as well at the time. Have you failed to reproduce somebody else's experiment? So these are just surveys. So they're not as rigorous as the previous evidence. But in chemistry, biology, physics and engineering, which would include computer science, I believe, medicine, earth and environmental science, look at these percentages answering yes. So well more than 50% in all these fields failing to reproduce somebody else's experiment. Yes. So Vicky says the devil is always in the details. That's true. That's very true. And we'll talk about that to some degree as well. And understanding why the experiments don't replicate. Yes, that's exactly the point. Another point, though, is trying to replicate the studies in the first place. So now I'm going to give a story about the importance of replication. And so as part of the story, I'll play a little video here. So in 350 BC, Aristotle sought to explain observed natural phenomena. In this case, why objects fall to the earth. Aristotle noted that light objects, such as a feather, they fall more slowly than heavier objects, such as a rock. Now, whether or not Aristotle actually used a rock and a feather in his example, we don't know. That part is apocryphal. But these are the objects of legend. At the time, of course, that Aristotle was doing this, there was no tradition of experimental science. Aristotle concluded that heavier objects fall faster than lighter objects. So the hypothesis was that acceleration in a gravitational field is proportional to mass. Now, this is wrong, but because Aristotle did not consider air resistance. But it was the accepted theory for 2,000 years. So a long time, this was the accepted theory. Heavier objects fall faster than lighter objects. I mean, look at the rock, look at the feather. So in 1600, Galileo tested Aristotle's theory by dropping things from the Tower of Pisa. Eventually, he dropped a musket ball and a cannonball. So these are both metal objects, very dense, and importantly, they have similar shapes. And he saw that the musket ball and the cannonball fell at the same rate. Now, this is also somewhat apocryphal as a story. We don't know if these are the exact objects that he dropped and if he actually dropped them from the Leaning Tower of Pisa or some other tower. But, this is the objects and the story of legend. He concluded that objects fall at the same rate. So in other words, acceleration is constant in a gravitational field. This we know today, of course, is the correct theory. So this is an example of the power of replicating a known experiment. Now the reason, let me stop these. The reason that I have told these two stories as an example of the power of replication comes from this video. So now I'm going to play a video that has sound, and I assume you'll be able to hear it, and then we'll talk about it.
Well, in my left hand, I have a feather. In my right hand, a hammer. I guess one of the reasons we got here today was because of the gentleman named Galileo a long time ago, who made a significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon? And I'll drop the two of them here, hopefully. They'll hit the ground at the same time. How about that?
Okay, so that was in 1971. And the person talking was David Scott. He was the commander of Apollo 11. This happened at the end of the last moonwalk. So still to this day, this person you see standing there on the moon was among the last two humans to stand upon the moon. And he dropped a feather and a hammer, and the moon has 1/6 gravity of the Earth. So you'll notice that the hammer falls noticeably more slowly than it would fall if you dropped a hammer on the Earth. And the moon has no atmosphere, so the feather and the hammer fall together. Notice that he also says in the little talk he gave, he says, one of the reasons we got here today, he's talking about Galileo, but he's also referring to the scientific process. Why is it that in 1971, a spaceship carrying humans was able to land on the moon successfully? Because of the scientific process. So replication is part of that process. And that's why we're giving this tutorial. Any thoughts about this? Yeah, we consented to have this recorded. I see a comment from Joachim. Yeah, we did. We consented to have it recorded, and it was recorded when we gave it at ISMAR in November as well, by the way.
Another question.
Another question? Falling objects. That's a good question. So the question from Pablo is, the replication by Galileo doesn't have the same conditions as the original. Is it a replication? It is. It's a replication
Yes.
with
Conceptual.
As Arifin will discuss, this can be classified as a conceptual replication. So it is a replication, but that is a good point. So now let's talk about inferential statistics and reproducibility. Now, you talk about inferential statistics when you take a statistics class, and that can get very deep. So we're not going, this is going to be a very high level overview of some of these issues. I think what I want to do is since the interesting stuff is happening in Discord, I want to put the Discord window closer Don't take over my screen. No, don't you do that. No, I don't like the way it tries to put things where it wants. Okay. All right. Okay. So what is the goal of hypothesis testing? So the goal, we collect a bunch of samples from some experiment, and we want to fit the population to those samples. So for example, earlier in my career, I was part of an experiment. Joe Gabbard and I ran this experiment where we showed some information in a virtual environment in stereo and in mono, and we were measuring whether or not stereo made a difference in the ability to navigate through that environment. So of course, we had particular people do the navigation, but we wanted to talk about what would happen for everyone who, saw stereo versus mono in this virtual environment. The whole population of everyone who has ever lived, who might do it now, who might ever live. So the population curve, that's what we really want out of most experiments, because that's how people will, this is what's going to be repeatable among different people. So that's the goal of hypothesis. Let's see, there's a window right next to the main screen in Verbella. Well, I'm not in Verbella to give this right now. That would be too distracting. So I can't see Verbella currently. So what are the possible alternatives when we run an experiment? So let's let the mean time to navigate be mu. So mu s would be the time in stereo, mu m would be the time in mono. So there are two possible alternatives. Perhaps there are two populations, and if there are two populations, then mu s and mu m could be close together, or they could be far apart. So clearly, if these two numbers are far apart, it's going to be easier to detect that they are separated than if they're close together. Nevertheless, in an experiment, there are two possibilities. Possibility one is that there are two populations. Possibility two is that there is only one population. So we're drawing all of these samples here from a series of participants, trials, etc. And it might be that the samples are being drawn from separate distributions, or it might be that everything is being drawn from one distribution. So this, in the most simple terms, is what it means to analyze the data from an experiment and subject it to a hypothesis test. So, oh, look at this. The bowling ball and the feather. Here's an evacuated chamber. That looks awesome.
There's a question with the back also.
Okay.
Yeah, that's based on the replication classification.
Yeah. Okay. So how do we test a hypothesis? So this is the logical structure of every hypothesis test. Every time you do a t-test or an f-test or a Friedman's rank test, the different kinds of tests that we do in empirical science. The same logical procedure, by the way, was done to validate the discovery of the Higgs boson at CERN as well, for example. So we develop a testable hypothesis. So subjects faster under stereo viewing, call this H1, the idea that the difference between these two means is some number, D. Then we develop a null hypothesis, which is the opposite. So that would be that there is no difference. It's the logical opposite of the testing hypothesis. We construct a sampling distribution assuming the truth of the null hypothesis. We run an experiment, we collect samples, yielding a sampling statistic that we'll call X. So that would be the time subjects take to get through this environment under stereo and mono conditions. Then, referring to the sampling distribution, we calculate the conditional probability of seeing X given the null hypothesis. So the probability of X given the truth of the null hypothesis. If that probability is low, then we are unlikely to see X. When H naught is true, we reject the null, we embrace the alternative hypothesis. If the probability is not low, so P greater than 0.05, is what we're usually looking for, we are likely to see X when the null is true, and we do not reject X. So a lot of the complexity of statistics is involved in calculating this conditional probability. But as long as we can collect it, we can go through this logical procedure. So here's the first example from a study that I did with Joe Gabbard a long time ago. So our hypothesis was that subjects were faster when viewing stereo. The null hypothesis that they were the same speed, whether viewing in mono or stereo. We constructed a sampling distribution, assuming the null is true. We ran an experiment, we collected these samples, and we found a difference this time of about 2 seconds, and it took 35, 36, 37 seconds to do the experiment. We calculated the conditional probability of seeing a difference as large as 1.983 seconds, given the null, and that probability was 0.445. So this is not low. We're likely to see a difference of this size when the null is true. Therefore, we did not reject the null. And this experiment did not tell us that subjects were faster under stereo viewing. So that was one experiment. Now, around the same time, we ran a separate experiment. Here, we tested whether subjects could respond to a stimulus under constant or decreasing intensity. This was an augmented reality. Our null was that subjects were the same speed, regardless of constant or decreasing intensity. We constructed a sampling distribution again, assuming the null was true. This time we had many times faster, responses. So we're looking at milliseconds. So under constant intensity, about 2592 milliseconds. Under decreasing, about 2339 milliseconds. So the difference here is 1/4 of a second. And the conditional probability of seeing this number, given the null, was only 0.008, so an unlikely event. So since this is low, we're unlikely to see a difference that large when the null is true. So we rejected the null, we embraced the alternative. So this experiment did suggest that subjects are faster under decreasing intensity. But of course, it needs to be replicated. So any thoughts about this? So did we check for stereo vision? Yes, we did. And Pablo is talking, he's responding to Tabitha. I can't really follow the thread of that question right now. So what does it mean to reject the null hypothesis? What does that mean? So when we calculate this, when do we reject the null? Generally 0.05, but I want to point out that this is just a social convention, and there is absolutely nothing mathematically notable about 0.05 or 0.01. It's just a convention that was adopted by early statisticians. When the Higgs boson was detected, the standard was much, much lower than 0.05. It was like, a factor of 10,000 lower or something like that, because the Large Hadron Collider was collecting hundreds of thousands to millions of observations during each experimental run. So that's an example of a situation where a very different alpha level was used. When we reject the null, can we accept H1? Boy, that's a good question. We're going to talk about that. So what can we say when we reject the null at 0.008? This is what we can say. And the reason we can say this is because it follows directly from the logical flow of hypothesis testing, which we have just looked at. If the null is true, there is only a 0.008 probability of getting our results, and this is unlikely. That is what we can say. Here's something that is often said in papers, but it's actually wrong if you consider the logical flow of hypothesis testing. There is only a 0.008 probability that our result is wrong, is an error. That's wrong because here it is referring to the probability of the null itself, and that's not what we calculated. See, when you are reading a paper, doing an experiment, this is kind of what you're thinking of. What is the probability of this hypothesis? But this is what you're calculating. Another thing that is also wrong is to say something like, there's only a 0.008 probability that the null could have been true in this experiment. That's wrong because it's turning around what's been calculated. This is referring to the probability of the null given what we've seen, but that's not what was calculated. What was calculated is the probability of getting what we saw, assuming the truth of the null. And isn't the whole point of doing replication experiments to see if the results previously reported are generalizable and apply to similar settings? Yes, that's exactly the point.
Exactly the point.
Yes, exactly the point. Yes, that's the point right there.
Mm-hmm.
So what does it mean when we don't reject the null? A question about this was asked a minute ago by Beatrice. Yes, Beatrice, I think. What can we say? Can we say that we've proved the null is true? Our experiment indicates that the null is true. Wrong. Hypothesis testing cannot prove the truth of the null. The reason is that the null, you're trying to assert that what amounts to a floating point number is exactly equal to a 0. Anyone who studied graphics knows that you can't take, say, two floating point numbers and ask, are they equal to each other? You can only do it within an epsilon boundary. You can tell if they're near each other, but you can't prove a point value is equal to 0. Statisticians do not completely agree on what it means to fail to reject the null hypothesis. So there's a conservative viewpoint that was initially espoused by Fisher, one of the person who first kind of conceptualized t-tests and so forth. Not the only one, but one of the main ones. And his point of view was that you have to suspend judgment. You can't say anything about the truth of the null. And that viewpoint has mostly been replaced by an alternative viewpoint by a pair of scholars in the 1930s, Neyman and Pearson. You can accept the null if you have sufficient experimental power and therefore a low probability of type 2 error. So, Arfan, why don't you just feel free to type stuff answering as well?
Oh yeah, I'm just reading some questions. It's related to that.
Yeah. So, so a large source of the testing confusion occurs because the reasoning behind hypothesis testing is inherently probabilistic, but the human mind is not good at thinking about probabilistic reasoning. We intuitively treat hypothesis testing as if the logical flow was absolute. So this is the logical flow of hypothesis testing. If the null is true, then X cannot occur. However, X has occurred. Therefore, the null is false. This is following the logical inference rule of modus tollens. If you take a course in logic, study logic and discrete math, you see these kind of truth tables. So modus tollens, if P implies Q, so if P, then Q, and then we assert that not Q is true, we conclude that not P is true. This is the logical flow right here. If the null is true, that's P, then X cannot occur, that's Q. So P implies Q. However, X has occurred, that's not Q. Therefore, the null is false, that's not P. So this is the reasoning if it was absolute. Now, let's look at a possible application of this reasoning. If a person is a Martian, then they are not a member of Congress. And by this, I mean the US Congress. This person is a member of Congress. Therefore, they are not a Martian. Is it actually the case that not every member of the US, that no member of the US Congress is a Martian? I mean, I don't know. Sometimes it seems like that might not be the case. Nevertheless, let's take this as a correct result. Okay. But all of this is assuming that hypothesis testing is absolute. Now let's look at another example of this. If a person is an American, then they are not a member of Congress. This is false. This person is a member of Congress. Therefore, they are not an American. Here, we are applying the correct logical reasoning, but we have an incorrect result. Okay, but all of this is assuming that hypothesis testing was absolute. Actually, hypothesis testing is probabilistic. So this is the logical flow of hypothesis testing. If the null is true, then X is highly unlikely. That's not the same as false. However, X has occurred. Therefore, the null is highly unlikely. The same reasoning, but it's probabilistic. It's not absolute. Now let's look at this next example. If a person is an American, then they are probably not a member of Congress. Now this is true. There are approximately 300 million American citizens. There are 550 members of Congress. If you do the division, you get 0.000002. So you would like to see a p-value like that. Suppose you saw this, and that was your p-value, right? Suppose you saw that. You would think, man, what a great experiment. But if you went out and chose an American citizen at random, completely at random, and you were asking, is this American citizen that I found a member of Congress? You know, this would be your probability right here. So we go up to the halls of Congress and we find a member of Congress. This person is a member of Congress. Therefore, they are probably not an American. So this is the incorrect result, but it's the correct application of the reasoning of hypothesis testing. Any thoughts about that? Okay, so the discussion is also thinking about other things. Interesting to see. So this is a beautifully discussed example of the logical flow behind hypothesis testing in a short paper by Jacob Cohen that helped influence my thinking about what hypothesis testing means. So now let's talk about power, effect size, and the p-value. So when you run an experiment, we have this 4-level decision table. And you get the same thing in signal detection theory. And in any case where you have this kind of 4-way process. So when we run an experiment, what is the true state of the world? What is the true state of the universe? Either the null is false or the null is true. And then we make a decision to either reject the null or not reject the null. Oh, yeah, you could paste the like the reference slide maybe if you want into Discord.
The paper.
Well, the Jacob Cohen. Well, you can just, I don't know. I'll let you do it.
Okay.
I'll let Arifin manage the Discord, or I'll get distracted. So since we have the true state of the world being true or false here, we either reject or we don't reject. That gives us 4 possibilities. We have 2 ways to be right and 2 ways to be wrong. So suppose that the null is true. So we're going to suppose that the bottom row is true. If the null is true, then we're drawing our sample from this pink distribution here. And we expect that the samples we draw will be centered around the mean, and it'll be less likely to draw our samples near the left and to the extreme right. We set our alpha level. And then if we see that our sample is to the right of the alpha, we make an error. Otherwise, we conclude that the null hypothesis is true. So if the null hypothesis is true, based on where we set this alpha, we either correctly accept the null hypothesis, although it's another question to argue it in a paper, or we make a type 1 error. We think we have a result, but we are wrong. This is the case if the null is true. So we're actually drawing from this distribution. Remember, we don't know if the null is true. We're trying to figure that out. If H1 is true, our sample is coming from this distribution. Okay, but we don't know where this distribution is. We assumed the null was true as part of the sampling statistic. So this line here is still our decision point. But if H1 is the case, then this probability beta, that's the chance that we make a type 2 error. Because if the sample we draw is to the left of this line, we are going to assume that the null is true, and that'll be a mistake. So that's a type 2 error. A result was there, but we missed it. Now, power is the more common term than beta. So power is 1 minus beta. Power is this part of the distribution here. But this is the meaning of the alpha level, 0.05, and then the power of the experiment, and the power is 1 minus beta. Any thoughts or questions about this?
So Dr. Gabriel is asking maybe the Cohen's book.
Yeah, it's actually, that's just a little paper, that last one. Yeah. Maybe just take a picture of that slide and paste the whole picture. Like
Yes, I can do that.
screenshot of that slide. So Arifin is going to post the screenshot of the last slide of this slide deck, which has all these references spelled, given. So in an experiment, we'd always like to increase power. And these little graphs here show you the 4 different ways to increase power in your experiment. So you can increase power by increasing alpha. So as you can see, if the distance between these two stays the same, but we increase alpha, then the probability of the type 2 error decreases. That means power increases, but the probability of a type 1 error increases. Likewise, if we decrease alpha, then the probability of a type 2 error goes up, probability of a type 1 error goes down. So when running an experiment, you cannot just set alpha to lower and lower levels free of charge. You're trading off the type of error that the experiment might make. So that's one way, is to increase alpha, one way to increase power. The second way to increase power is to measure a bigger effect. So if the effect size is large, that means that the distance here will increase. So when the effect size is large, power goes up, type 2 error goes down, probability of type 1 error stays the same. So unsurprisingly, a big effect is easier to measure than a small effect. Unsurprising. We can also increase power by collecting more data. So these are normal distributions. The error area under each of these curves is equal to 1. So when we increase the sample size, the distance here stays the same, but the distributions get taller and narrower. And so when we increase the sample size, the variance decreases. That's the distance of the distribution. The power increases. The probability of a type 2 error goes down, and alpha and type 1 error, those stay the same. And there are techniques that give the value of n, that is the sample size required for a certain level of power. And so the most common use for power analysis is to determine a sample size. So if we expect a certain effect size, this is how many participants we're going to need in order to detect that sample size. This is also the way to argue the null hypothesis. So that question was asked earlier, I think by Beatrice. The second way, another way, the fourth way, actually, yes, the fourth way to increase power is by decreasing noise. Notice that collecting more data and decreasing noise are exactly the same in terms of power. So when the experimental noise is decreased, the variance goes down, and all of these things remain the same. Probability of type 2 error goes down, probability of type 1 error stays the same. So more careful experimental results give you lower noise. So this is why it's important in your experiment to make everything as clean and carefully done as you can, because the lower your noise, the higher your experimental power. Of course, that's also a trade-off because low noise kind of enhances these laboratory experiments that deviate more and more from real world situations. So that's also a trade-off. So how do you use power if you're an experimenter? So power is really a 4-way interaction based on the non-central F distribution between power, the alpha level, the effect size, and the sample size. And in our field, it's hard to know effect sizes. One way you do learn effect sizes is through replication studies. But our field is relatively new, not many prior studies, not many replication studies, so it's hard to estimate effect sizes. You can find effect sizes in more mature fields. Some of our experiments are based on previous experiments in psychology, and there you have some ability to measure an effect size. Sometimes experimenters are tempted to engage in post hoc power analysis. That's where you estimate your effect size from what you found in your experiment. And then you calculate the power for the experiment. But this makes statisticians grumble because this is going to have the same information as the p-value. So if you have a very low p-value, you're going to have a larger effect size as measured by subtracting the means in your experiment. If your p-value is higher, this is going to be lower. And so it is not meaningful in an experiment to report an effect size based on the difference in your calculated means and then use it in a calculation like this. Of course, you should report these effect sizes because those are the findings of the experiment. How much faster or slower were people in stereo versus mono? But you should not use that number to calculate the power. It's the same information as the p-value. So the main use for power is here, the number of samples needed for a certain power level. And Cohen has a recommendation that's been pretty widely adopted. If you can do a power analysis, you set your alpha level to 0.05 and your power to 0.80. So the probability of a type 2 error is about 4 times the probability of a type 1 error. That's what Cohen recommends. But this is a relationship between 4 numbers. So you can also calculate the effect size that will be detectable. This is how you argue the null hypothesis. This right here. That's how you argue the null. The significance level needed. And number 1 here is the most common usage of the concept of power in experimental design. So let's talk about arguing the null hypothesis directly. You cannot argue that you found this point value, the null equal to 0, but what you can do is you can argue that the size of this interval is less than d. You can bound it by an effect size d. If d is small, and what does small mean? That depends on the context of the experiment. So if I'm looking as Joe and I did, if we're looking at stereo and mono in a virtual environment navigating through, and it's taking people about 35 seconds, we have to decide what effect size is so small that it no longer matters. 2 or 3 seconds? At some point, it doesn't matter. And so if you can argue that d is small enough, you've effectively argued the null hypothesis. I see a mistake here. Alpha 0.05, this should say beta equals 0.20. Instead, it says power. So that's wrong. Make a note to tweak this slide before I post it for posterity. What slide is this? This is slide, I don't know what slide it is. 27.
27.
Yeah. Okay, make a note of that. Okay. So I'll see the mistake, right? Power here, that should be 0.80, not 0.20. So at this point, been talking for about an hour, and the next stage is going to be talking in detail again about the reproducibility project, psychology, We have one continuous 3-hour block, but I'm going to declare a break for about 5 minutes. I'm going to go get some tea, and we can all take a break. And I'll see you all in 5 minutes. So Nahal is asking about experiments with lots of different p-values. How do researchers use effect size in studies with a lot of conditions where there can be a lot of significant differences? So there is something called the family-wise p-value that can be calculated. And I think this is a statistical way to take into account asking many different questions, that is running many different hypothesis testing in the same experiment. See, I think I can respond to this. So you set an alpha value, you call it the family-wise alpha value. And that is used for experiments with lots of different hypothesis tests in it. I think that's what the question is talking about. So I'm going to talk now. So I'm live, right? I think I'm still live. I'm going to talk now about the reproducibility project in psychology. And so, as we saw previously, there has been this this series of reproducibility efforts in medical science and in psychology. And so we're going to study now in some detail the reproducibility project psychology. So this project was begun by Brian Nosek. He's a professor of psychology at the University of Virginia. And he's become quite well known in the reproducibility scholarship area through this project. And he became an academic star from this project, really. And I'm going to show you something else. I have to find it. Here we go. Preview and window. There we go. So this is the paper, the reproducibility project psychology, that we're talking about now. So this was a paper in Science. It's called Estimating the Reproducibility of Psychological Science. So this is the paper that we're looking at. And this is a result of this project, the reproducibility project in psychology. In this project, exactly 100 published studies were replicated. A very large team was recruited. So the final project has 270 co-authors. So I think you can still see my screen when I show this. Okay, good. Sometimes, thank you, Arifin. We now have tea. I will sip my tea. That's good. Okay. So this paper has 270 co-authors. Notice that I'll make it bigger here. Notice that the author is the open science collaboration. Okay. And if we go down to the end of the paper here, okay, what is the open science collaboration? These are the authors of this paper. You ever seen a paper with this many authors? Now, the original paper to report the original human genome, that is something like 1,000 authors, but there's Brian Nosek, you know, just alphabetically in the list of authors. And then here's all their affiliations and stuff. So very interesting paper. So the first goal of this study was to choose which studies shall we replicate? So the team wanted to minimize selection bias, maximize generalizability. So they published a plan before doing the experiment. They said, we're going to do this experiment. That's a smaller paper that was published somewhere else. I'm not sure where. I mean, it's in the citation list. And they published a sampling frame and selection criteria. And so they decided that they would replicate studies that were found in 3 leading journals in the field. Those journals were Psychological Science, the Journal of Personality and Social Psychology, and the Journal of Experimental Psychology, Learning, Memory, and Cognition. So psychological science is considered, at least in Brian Nosek's field, as the premier outlet for all psychological science. JPSP, this one, that is considered the leading journal for social psychology. And then JEP, LMC, and these abbreviations are what I see written. So JMC, LMC, that's the leading journal for cognitive psychology. So the goal of the journals selected is to avoid, well, let me show you this. So the sampling frame is, they take the first 20 articles in each journal, beginning with the 2008 issue. And they're going to attempt to replicate the experiment in the first 20 articles. They generally try to replicate the last study in the article, because articles that report multiple studies is typically the last study that's like the main point of the paper. So unless it was infeasible, they tried to replicate the last study in the article. 84% were the last study. So the first 20 articles in each journal, each of these 3, then 10 more articles as necessary to create the total number of results they tried to replicate. The result to be replicated must come down to a single inference test, hypothesis test, usually either a t-test or an f-test or a correlation. And if available, they would use the original materials for the experiment. They would get the original materials from the authors. One reason for 2008 was they wanted articles old enough to have some citation history, but new enough so that the original authors were still there to talk to and the original materials were available. And the design of the experiment was reviewed by the original authors. And using the results from the original experiment to estimate a effect size, all experiments were conducted with enough participants to have high statistical power. So power was 0.80 or higher, as recommended by Cohen. So this is the effort, a monumental effort. You know, imagine trying to replicate more than 100 previous experiments. I mean, that's what this group did, but 270 authors. So it was a large effort, quite a large effort. So the results were 488 articles in the 2008 issues of the 3 journals. 158 of these were available to be replicated. 113 replications were selected and attempted, and 100 were completed by the deadline to make it into this paper. So by chance, exactly 100 studies were selected to be replicated. So questions that arose in this effort: how do we measure a replication? How do you measure that? Arifin is going to talk about this in some detail after I finish. How do we measure a replication? How do we quantify a series of replications? So each experiment was analyzed with a standard R package. I have to say I approve of that. And each analysis was performed independently by a second team. So the team that was doing the replication would analyze their results, but then they would send all of their data to a separate team, and there the results were independently analyzed and the two compared. So these are what was studied in order to measure replication. So the original study had the following characteristics. The original study had a p-value, had an estimated effect size, had a sample size, or if it was a repeated measures design, the degrees of freedom, which has to do with the number of subjects and then the number of samples per subject. A rating of the importance of the result. So all of the other participants in this experiment, in this 270 people, they said, how important is this result? How surprising is this result? And what is the experience of the original team and the expertise? So all of these were rated. Then for the replication, that also produced a p-value. It also produced an effect size. It also produced a sample size or degree of freedom. You could determine power from the replication because it's built on the original. The team rated how challenging it was to perform the replication. The experience and expertise of the replicating team was also assessed by all other authors. And the quality of the replication was also rated. So these were the statistics that were collected about the original experiment and the replication of the experiment. Any questions about this? I see some folks are typing, so I think questions are coming. Okay, so now I'm going to talk about the results of the replication study. We're going to look at the results in 3 different graphs. And these are really beautiful graphs, and I get excited about graphs. My original field of study was visualization. How did 270 authors deal with conflicts of interest? Yeah, so I believe this is discussed in the paper, but yes, that's an issue right there, definitely an issue. So, so first, this is the p-values that were measured. So these are violin plots. Here are measured p-values, p-value from 0 to 1. And this dotted line is the 0.05 level. So this is what you want to see. And the dot here is the median p-value. And then the violin plots show quantiles. So the first quantile is squished and very hard to see. Here's the second quantile, the third quantile, and the fourth quantile. And so violin plots are like a visualization of the shape of the distribution. So for the original studies, you can see that the p-values were very low. So for the original studies, all of the reported p-values were less than 0.05, except for 4. Those 4, which is indicated by the small shape here above the dotted line, these 4 had p of less than 0.06, but that result was treated as significant in the paper. And for the replications, as you can see, the median p-value was up here about 0.2. And look at the p-values that the replications spanned. So there are several statistical comparisons given in the paper But the result is visually obvious here. The replications had much higher p-values, much higher. You can see it. Okay, so this is one measure of results. Here's the next. So now we're looking at effect sizes. So all of the effect sizes were turned into correlations, correlation coefficients. So correlation coefficients always vary from -1 to +1. And the original studies were designed to always have a positive effect size. So the effect sizes range from 0 to 1 for the original studies. And there's our median value and our quartiles. So these are the effect sizes in terms of correlation. And here are the effect sizes of the replications. And so where a study went from a positive number to a negative number in terms of effect sizes, that's like your hypothesis is that, say, stereo is going to make people faster, but when you replicated it in stereo, people were actually slower. So that would be a flipped effect size. You get the opposite result of what the experiment hypothesized would happen. So the visually obvious result here also follows from here, and that is that effect sizes for replications went down quite a bit. Out of 99 studies, effect size went down for 82. And then there was one study out of those 100 that did not allow for this calculation somehow. Now here's the third graph that gives the results. This is a very beautiful graph that packs a lot of information into one visualization. So I'm quite enthused about this graph. So this is comparing effect sizes in a different way. So here are the original effect sizes, these little dashes here, 100 of them, the original effect sizes ranging from 0 to 1. Up here is the probability plot of the original effect sizes, the density plot. So the blue are for the significant results, 0.05 or less. And this, which is red here, that's for the 4 that were above 0.05. So that's this source right here of data. Here are the replication effect sizes along the y-axis. These go from -0.5 to 1. And this dashed line here is the 0 level for the replication effect size. Here are the same two probability plots for the replication effect sizes. So the significant results and the insignificant results. Notice what happened between this set of probability plots and this set of probability plots. That is essentially another way of visualizing these results right here. Okay. Now, this line here gives the 1-to-1 ratio between original effect size and replication effect size. All of the experiments are also represented as dots here, where the dot is a blue color, the replication was a success, was a significant value. And the orange dots, I guess these are kind of a dusty rose color. You know, these were unsuccessful replications. So notice that the successful replications are kind of clustered around this line. Where a dot is above the line, that means the size of the replication effect size is larger than the original effect size. So dots right on the line, the effect size would remain the same. All of these dots below the line, the effect size declined. So the results are visually obvious here as well. The effects, the replications had lower p-values, lower effect sizes, and many of them, the ones in dusty rose, were not successful replications in the sense that the experimental value had a p-value quite a bit higher than 0.05. Any thoughts or questions about this? Okay. So now we're going to look at the results by percent replicated, broken down in several different ways. So the initial strength of the evidence for each experiment predicted replication success. So remember I mentioned that the lower the p-value, the more power the original experiment had. And that shows up here. So for p-values that were below, equal to, or less than 0.001, 63% replicated. That is, the replication had a p-value of 0.05 or less. When p was less than 0.02, 41% replicated. Oh, yes, you can make such a figure in RStudio with ggplot and maybe other tools as well.
Oh, yes.
Yeah, you can definitely create such a figure. I'm teaching a class right now where we create such figures. For the p-value between 0.02 and 0.04, 26% could be replicated. And for original p-values of 0.04 or less, only 18% could be replicated. So initial strength of evidence predicted replication success. Unsurprisingly, the stronger the original findings, the more likely they were to be replicated. Another finding, I could tell from the writing in the paper, this part was written very carefully. This was a controversial thing to say in the field in psychology, but cognitive psychology was generally more successfully replicated than findings from social psychology. So 50% of the cognitive psychology results were replicated, but only 25% of the social psychology results. So there were weaker original effects in social psychology. And that could be because social psychology effects, things like, measurements of personality and things like that, it's harder to measure. These are like higher level cognitive phenomena, harder to measure. In addition, cognitive psychology tends to have more within subject repeated measures designs, which give you more experimental power. So main effects were more successfully replicated than interactions. So 47% of the main effects were replicated, but only 22% of the interactions. So this is also to be expected because main effects typically have higher power and are more repeatable than interaction effects. Well, were more repeatable because they have higher power. Now, here's some of the most interesting results of all for this audience on this slide. So here, we're going to give a series of results, correlation with replications. Okay. So surprising effects were less reproducible. I think this is important for our field. So the surprisingness of the original result was negatively correlated with reproducibility. The more surprising the result, the less likely it could be replicated. But journals and conferences like to publish results that are surprising. However, this shows surprising results are less likely to be real effects. Challenging experiments were also less reproducible. This is less of a surprising result. So challenging experiments, more difficult to replicate. the importance of the original result, how important people rated the original result, that had little effect. So slight negative correlation. Didn't really matter if the original result was rated as important or unimportant. The team experience and expertise had almost no effect. So basically, all of the teams had the proper experience and expertise to conduct the original experiment as well as the replication. There was really no effect of team experience and team expertise. And the rated quality of the replication had essentially no effect. So these are all the negative correlations here. All of these are negative. The positive correlations were the results that we've already seen. So larger original effect sizes were more reproducible. Come on. Larger replication effect sizes were more reproducible. And more powerful replications were more reproducible. That's what we saw visually. So to summarize, even though the replications used the material from the original authors, were reviewed in advance to have the proper methodology, and had a high statistical power to measure the original effect size, so power of 0.80 or higher. Even though the replications had all of these properties, the replications as a whole produced weaker evidence for the original findings. The strength of the initial evidence as measured by p-value, as measured by effect size, that is what predicted replication success. The characteristics of the teams and the original findings had no impact on the success of the replication. So this is the main summary of the findings right here.
Yes,
I've seen many review comments about unsurprising results. Yep, that should be included in reviewer instructions. I think there is now language in reviewer instructions about replications, but we're going to talk about that in a minute as well. Yes, unsurprising results. Yes, I've gotten those comments myself, as you will see. So why were there so few replications? The result that we discussed at the beginning of this tutorial said that it had to do with publication, selection, and reporting biases. So publication bias, only significant results are published. Selection bias, only significant results are selected for analysis. Reporting bias, only significant results are reported in the paper. Therefore, the effect sizes of the original studies were inflated. The replications, on the other hand, all results were reported, so there's no publication bias because they're all reported. All confirmatory tests are based on pre-analysis plans. So that means there is no selection and no reporting bias. So the structure of the replications took into account all of these biases. No publication bias, no selection, no reporting bias. So the lack of biases is the big part of the reason why there were so few replications. So this is the reproducibility project psychology. It's a very well-written paper. I read it very carefully and got inspired enough to put together this tutorial about what I read in this paper. I first gave this tutorial at VR 2018, so 3 years ago, right about now. Then I gave it again, VR 2019 in Japan. I gave it in the fall of 2018 at ISMAR. And then a year ago, Arifin joined me to, no, when did you join me?
ISMAR.
Yeah, I didn't give it last year. That's right. Not at VR 2020. I gave it at ISMAR 2020 along with Arifin, and now we're giving it again. So a very good paper. I recommend it. So what does all this mean? That's what we explore next. What does it mean? So let's consider for a minute now, why might a finding be irreproducible, not able to be replicated? So we have some study and it finds A. A is a finding. But the replication study does not find A. Why could this be? Why? One idea is that the original study is wrong. In that case, A is not true. So that could lead to this situation. The original study is wrong. A is actually not true. Another reason, the replication study is wrong. In this case, A is actually true. So the first study is correct. The second study is wrong. But the third possibility is that both the original study is correct and the replication study is correct. And in this case, A could be either true or false, and the combination of both studies hasn't fully revealed the truth value of A. There was a comment on the Discord that reminded me of what we're talking about on this slide. That comment was pretty early in the talk. I can't remember who made it, but this is getting to this idea here. So how could number 3 be the case? Number 3 is the curious one here. It's obvious that if the original study is wrong or the replication study is wrong, you know, that's obvious. But the third one, how could they both be correct? Okay. So this was the point of the Discord message. You know, many things can differ in an experiment. The experimenters can differ, the participants can differ, the methods, equipment, analysis can differ. You can also have random variation. So we've talked about the type 1 errors, the type 2 errors. So these are real errors. In this example here, the story of Aristotle, Galileo, and then astronaut David Scott. Number 3 is the case. So the original study was correct, considering the effect of air resistance. Aristotle didn't know about, but it was correct. The replication was also correct, also considering air resistance and the fact that 2 objects of the same shape were used, you know, 2 metal balls. So both were correct studies. In the case where A was Aristotle's original theory, A was wrong, A was false. So some reproducibility scholars, including Brian Nosek, believes that number 3 is the most common case, the most common reason for results to be not reproducible. Both the original and replication are correct, but there are differences in the experiment, and that's why. Any thoughts about this?
Several people are typing.
So Regis is saying, should we just do without critical values and only focus on effect sizes? Perhaps, but a p-value is also a measure of effect size. So yes, there you go. More replications are necessary. That's going to be the punchline of this whole tutorial. Exactly. Okay. So first impressions are often false, and it can be hard to detect the difference between a real result and noise. So some slides ago, I showed you the diagrams of the two probability distributions. So when those two distributions are close together, it's hard to tell the difference between a real result and noise. This is related to another point that was made on the Discord. If enough hypotheses are conducted, you can usually find something. That's true. If you run a whole series of tests in an experiment, you know, some are going to show up. Some are going to show up as significant just by chance. This can be controlled by adjusting something called the family-wise alpha level. And I'm just citing the stats book where I first read about that. But the larger reason for irreproducibility is what we started with. The incentive structure of science, including the incentive structure of our own field, of our own conference, of our own research community. The incentive structure does not maximize the yield of true results. So we are incentivized to find significant, novel, and surprising results. Significant, novel, and surprising results lead to papers, leads to funding, leads to degrees, leads to career advancement. And these incentives, how you get papers published, how you get funding, how you get your degree, how you become an associate professor, a full professor, a senior scientist, etc. How these things happen results in many exploratory studies. And this is true in our field, and it's true for every field of science. If a finding is spurious, we don't know that until a replication is attempted. So now there's quite a nice long comment, but I don't have time to read it. I'm sorry. I'll try to read it more carefully in a bit. Yeah, valid clinical VR content. Yes, I'm sure there are methods from measuring things clinically that could also be used. So a study finds A, the replication finds A. What does this mean? So we successfully replicate something. What does that mean? It means that A is reliable. It means we can repeatedly find it. But what about the theoretical explanation for A? So that explanation might still be wrong. So this is another moral of this story. So this experiment is very repeatable. You could go out today with a rock and a feather and repeat it. You could also drop a cannonball and a musket ball, if you had such things around your house. You could drop them and they would fall at the same rate. So both of these experiments are perfectly repeatable. If you went to the moon, this would be harder to replicate, but you could replicate it if you got to the moon. You could drop the feather and the hammer on the moon. So, it's the explanation that can be wrong, even when an experiment is repeatable. So understanding the reasons for the finding requires multiple investigations. These multiple investigations provide converging support for whatever the true theory is, and they rule out alternative and false theories. How frequently are studies replicated? So that's a great question, and Arifin is going to talk about that. That's the fundamental topic of Arifin's component of this tutorial. So we're going to be considering that in quite some detail in a few minutes. And I will be done in about, 10 minutes. Do we have any statistics for the AR/VR field? Yes, we do. Arifin will reveal them.
Yes.
We have these statistics, by the way, because of Arifin's personal scholarship in this area. No one else has really systematically looked into this, but Arifin has, and this will certainly be a paper that we'll be working on,
Yeah, we're still working on that.
in the coming months. So here's another philosophical question for everyone. How many studies should be reproducible? So the replication project in psychology reproduced 36%. Is this too small? It seems like it's too small, How many studies should be reproducible? But it's unclear what this number should be. What would 100% reproducibility mean? If everything was reproducible, it means we would never be surprised by anything. It would suggest we always knew what would happen and why it will happen. So why would we be running the experiments in the first place? So 100% seems like it's too high, but 36% seems like it's too small. So progress requires both reproducible experiments, but some that are not reproducible. So the perfect reproducibility percentage is probably field or subfield dependent and is almost certainly unknowable, probably higher than 36%. So progress in any empirically scientific field, such as the human subject side of XR, it requires both exploratory studies where we have innovative new ideas and confirmatory studies. These are replications. Confirmatory studies are what we don't have enough of in our field. The innovative studies point out the ideas that are possible, but the replications point out the ideas that are likely to be true, and progress in the field requires both. It's not enough just to explore possibilities. We also know what ideas are likely. Okay. The scientific incentives, funding, publications, awards, advancement. This ideally should be tuned to encourage an optimal balance in a collective effort of discovery. So there is no quantitative answer to how many studies should be reproducible, but probably more than 36%. So the last component of my talk, of my part of this tutorial, that means you're going to have about an hour.
Oh, that's fine.
Yeah, for your part, and of course for discussion and stuff.
Oh, yeah, I think I'm not like an hour, like 40, 45 minutes.
Okay. All right. So the last part. So what should we do? We, in this research community, what should we do about this? So my main point of this whole tutorial and of studying this paper and talking about the statistics, within it, is to value replication studies. So we want to value confirmatory studies. We want to value replication studies. We should also value exploratory studies. We already do value exploratory studies. That's the primary source of our studies. The largest point is to value studies that are well done, regardless of the type of study or the type of results. And that requires changing our incentive system. Now, somebody was talking about reviewers complaining about surprise. Okay, now I'm going to show you some sentences that I've had reviewers enter for my own papers. So as people collectively running this conference, well, before I talk about that, I'll show you this. So My own empirical experience involves about 25 years, more than 25 years of conducting empirical studies. Originally, I conducted experiments in HCI and then started doing them in virtual augmented reality. And I've been publishing this kind of research since 1993. For the past 8 years, I have served as the general chair of this conference twice now. And before that, I was for 4 years a program chair for IEEE ISMAR and then IEEE VR before that. And I have seen, therefore, examining the decision process for papers, entirely too much emphasis on novelty and surprise in the review process. So here are 3 comments that came from negative reviews that I have received on papers. Not all of these papers were rejected, but not all of the papers from which these comments came from were accepted, at least not, the first time they were submitted. And I am definitely not trying to say that all of my own papers should be accepted. But, there is this bias, this emphasis on surprise. So here are these comments, which I copied directly from the, from the reviewer comments. So rather a reduction in the availability queues, which makes the reduced performance not terribly surprising. This experiment tells us something important about depth perception in AR, most of which isn't especially surprising. It is not clear that this will help very much. It is not entirely surprising that participants became more accurate in the feedback conditions. So many of us have gotten comments like this, yeah, it's nice you did this work, but it's not surprising. So why, it should not be accepted. So as people collectively running this conference, we can't directly control things like how our funding agencies work, how the advancement systems operate in our places of employment. But we can control how our review system is conducted. So there has been some movement in our field towards more of an awareness of the importance of confirmatory studies, of replication studies. And I saw some of that language in this year's call for papers and so forth. And I applaud that and think it's a good thing. And a big part of this tutorial was making a case for less emphasis on surprise and more value for replication studies. So, and Regis says, shouldn't reproducibility be a requirement for the scientific method? Well, in empirical science, it definitely is a requirement. So the recommendations are to value replication studies. We operationalize value by accepting them. If they are accepted, people will do them. Another replication is to pre-register research plans. So before collecting data, create a detailed written plan with a hypothesis, methods, analysis. If you're working on a thesis, dissertation, this is often what your proposal document looks like anyway. And this removes the possibility of p-hacking, where only significant results are sought and published. Even better is to publicly pre-register the plan. So that is possible at several different places. So there is a Brian Nosek and his group started a organization called the Center for Open Science. And this is their webpage. So this was developed by this group. And it has a place where you can pre-register an experiment. They also have a pre-registration challenge. And I don't know if the pre-registration challenge is still operating, but they got a grant, $100,000 grant, and the first 100 registered experiments were getting like $1,000. for pre-registering the experiment. So pre-registering research plans is another idea. Let's see, an interesting thought about our field is let's see, there's two interesting comments. A lot of work needed from the reviewers to prove reproducible content, to provide, I think, provide reproducible content. So that is another part of the recommendations, is to make sure that enough details are available so that experiments can be reproduced. We want to use the best and newest technology. Yes, we do.
So that's
And
a nice question. Actually.
yeah, it's a great question. Austin Erickson asks, new hardware is coming out so frequently. We have many different displays. It makes it difficult to replicate. Yet at the same time, yes, this is very true.
Very true. Very true. It's a very nice question.
Here's another, yes, very nice question. Here's another problem that we've wrestled with in our own lab. So you have this Microsoft HoloLens display, and it's constantly updating itself. So the fundamental underlying algorithms that it's using are changing while your experiment is progressing. And then you've written your code in Unity. How often is Unity updated? I mean, like every week, right? So, you know, Unity is changing. I mean, so what we've tried to do in our lab is kind of create isolated private networks so that nothing can replicate while we're collecting data. And then the system administrators come by and say, oh, you can't do that. You got to let everything update, because they think that, you know, the whole purpose of all this stuff is to collect viruses and things like that.
Security purposes.
Yeah, security purposes. So that's a big challenge. Not only is the hardware constantly changing, but the software that runs the hardware is constantly changing. I mean, like week to week. So that's a big challenge, a really big challenge. Absolutely. Another recommendation is to run studies as large as possible, more participants, more experimental power, but of course, more expensive. More expensive. Another recommendation is to describe the methods in more detail so that replication is easier. A problem in our field is limited pages, but there are solutions. Additional details can go in supplementary material, or it's very common. I have all of my students who, you know, write a thesis or dissertation. Of course, we cite that and indicate that more details can be found in the thesis or the dissertation. We could also adopt longer page limits. I don't know, this is a recommendation that goes two ways, because as readers, you want to kind of get a brief summary. You want to, you know, have a paper that makes its point. So I think supplemental material that people who really want to delve into the experiment can get into is probably better than longer page limits. Another idea that comes from various journals, including the journal Nature, is to put the main paper in a bigger font and the methods section that contains more of the experimental details in a smaller font. I think this is a very useful idea, and I'm going to show you an example of this. So here's a paper that in my lab has been cited a good bit. It's in the journal Nature, Perceiving Distance Accurately by a Directional Process of Integrating Ground Information. And I don't want to talk about the contents, but notice the way the paper is typeset. So here is the abstract. Here is the meat of the, and this is all written kind of at a higher level, a level of, you know, the science itself and the results and diagrams and results and more diagrams and results. And then at the end of the paper, see, there's this square indicating this is the end of the paper, but here's details. So here are the methods section. See how it's a smaller font. These are like additional experimental details that kind of get in the way of the scientific story but are necessary to replicate the experiment. So that's a typographical convention in other fields, and we could consider such a convention in our own field. There is a big push, including at TVCG and IEEE, to upload materials to open repositories. And so this would include data, materials, and code. So there is the Center for Open Science that I just showed you. There is also the TVCG replicability stamp. So if we go here, so the idea here is that your TVCG paper would have a stamp on it saying it's repeatable. And this has been in effect since January 1st of 2018. Now, this is talking about uploading your code. This is talking about algorithmic repeatability. You know, your code, your operating system, you know, the versions of things that you used, the version of the operating system that was running on the HoloLens, things like that. But the point is, you know, there is efforts even at TVCG and IEEE around repeatability. There's also the IEEE data port. This is a place where you can upload your data for posterity to be repeatable, and IEEE Code Ocean. So Code Ocean is interesting because they use virtualization technologies to freeze things like the version of the operating system that you used to compile your code, the version of the libraries, you know, behind the code, things like that. So it's all in the service of reproducibility. See, code, environment, data, result. Now, you know, you can't cache your users here, but you know, the point is that within IEEE, there are efforts towards reproducible research. A larger definition of reproducibility. This tutorial is centered on human subject reproducibility, but you know, there's a larger issue around it as well. There's also archive, preprint servers, things like that. So that, whoops, I clicked the wrong thing. I meant to click on the slide itself to advance it. So reasons for optimism. I'm an optimistic fellow, especially when I have a few beers. All right. So the current zeitgeist among the journals, funders, scientists, all paying more attention to replication, statistical power, p-hacking, etc. In psychology, journals have begun publishing pre-registered studies. Yes, there's a graphics replicability stamp initiative. Yes, that's what the TVCG is part of. It's this graphics replicability stamp. Scientists from many labs have collaboratively replicated earlier studies. So that's been happening. And the Center for Open Science, showed you a snapshot of that website. And I told you about the 1 million, I said it's 100,000, but it's actually 1 million to pre-register, you know, their pre-registration challenge. And the goal there is to get people to try pre-registering for the first time. So this is the end of my presentation. These are the references, which Arifin posted a picture of. And at this point, Arifin and I are going to trade places. You want to have a pause first, or are you ready to just go?
It's up to you. You can give us some break, 5 minutes. Or...
Let's take a 5-minute break, and then Arifin will present. And his stuff is much more like centered on our field exactly. So I'm going to put his slide up, and Then we'll take a quick break. Let's see.
So hello everyone. Thanks to Dr. Ed for an excellent presentation. Oh, I really learned a lot every time I saw his presentation on this tutorial. That was really excellent. So I'm Mohammad Arifin. I'm a PhD candidate from Computer Science and Engineering Department at Mississippi State University. So I'm doing my PhD under Dr. Ed Swan. So he actually encouraged me, and I got encouraging words from him to work on this, and I found this is very cool. And working and the behind the replication crisis in empirical science. So in my talk, I mainly focus basically mostly on each what is going on related to our field and what kind of a different kind of replication we find. So in the beginning of my presentation, some things can be overlapped with Dr. Swan's talk, and then I will talk about different types of replications, and then uh, what's actually happening in replications in human-computer interaction, human factors research, and obviously in AR and VR. So started with the studies and empirical research. So when you think about the studies and empirical research, we think about the experimental studies. So these studies can have two types, exploratory studies and confirmatory studies. So exploratory studies actually bring possible new ideas and innovations in a particular research domain. On the other hand, the confirmatory studies confirm a previous findings or results by doing some replication. So in a particular research community, there should be a balance between these two type of studies to consider contribution to that particular field. So from that confirmatory studies, the word replication actually comes. So the question is, what is replication? And there is a paper on that. That's the title, What is Replication by Nosek in 2020. So according to our common understanding, replication is like a repeated previous studies procedure and observing whether we are having the same results or not. However, this definition is very intuitive and total, this is incomplete, you can say. So Nosek, that person actually provided a more complete definition of the replication study. He said the replication is a study for which any outcome would be considered diagnostic evidence about a claim from prior research. So that outcome can be successful, that outcome can be unsuccessful. So what actually the benefits of successful outcome? So the successful outcome actually telling us that, okay, the prior research is successfully replicated, it provide more confidence on the result of the prior research and make the things more generalized. But what about the unsuccessful replication? Is it like totally useless? The question is no. So unsuccessful replication also provides us some diagnostic evidence. It's actually telling us that, okay, we need to do more study on the prior theory, which is established by the original study. And it also indicates that maybe there is some constraint having the original study can have. So we need to explore more. So this is not totally useless. But this unsuccessful replication brings an issue named file drawer problem. So this term actually provided in 1979 by Rosenthal. So what actually the file drawer problem is? The file drawer problem is like publication biasness or only celebrate the successful research. So when we are having a successful replication or successful research, we always try to publish it, and if we always try to celebrate it. But in unsuccessful replication, so that means if you have unsuccessful replication that can put in someone drawer and you say that, okay, maybe I did this work, but I'll not be able to publish it, some like thing like that. So this brings the issue of file drawer problem from the unsuccessful replication. So what actually the general goals of a replication study? So the general goals is to verify, validate, generalize, and establish a prior theories or hypotheses or models or finding in the research community. Therefore, when you have an original study, when you want to do a replication study, you should have at least one of this intention while performing the replication things. So the next thing is the replication topologies. So previously I just said there's some basic interaction. So that interaction actually of all of Dr. A discussed in very details. So from here, I'll tell you like different kind of replication topologies. So the interesting fact is there is no general replication classification. This classification based on your the research discipline from which background you came from. So I found a paper in the published in 2010. The paper is replication types in experimental discipline, and that paper found 18 replication classification, just the classification. And from that 18 total classification, I found like there are total 79 replication types, which is quite a lot. So, and they mentioned that most of the classification are coming from the social science, and then from the business, then from the philosophy, like this. It's actually not a general thing. It's actually depending on your research field and your research domain. So they provided this chronology, classification chronology. And if you look at that, the social science, that's the oldest one. It actually, first one is provided around 1968. So those are very old replication classification. So for this tutorial, I consider the most often cited classification, which is the Lycan one and the Hendrick one. So these two classification actually used in many papers and most often cited classification. So let's start with the Lycan's classification, which was provided in 1968. So he divided the replication into three types. So literal replication, operational replication, and constructive replication. So the first one is the literal replication. So it means that doing the exact replication of the original investigators, sampling procedure, experimental condition, measuring techniques, method of analysis, everything like as exactly as possible. It's like asking the original investigator to simply run more subject using the same thing. Operational replication. So this is like a slight modification of your original study. So it's like this, the main experimenter of the main paper did an experiment. Now you have experimental recipe and you are now want to do the same experiment and try to publish a similar type of result. Therefore, the thing is to test whether the original investigator experimental recipe will in other hands produce the results that he obtained. So same experimental recipe, same thing, but doing some different people, not the same people. So this is the operational replication. The third one is the constructive replication. It means replicator formulate his own method of sampling, measurement, data analysis to investigate whether the prior finding is established or not. That means he's investigating the prior theories and prior research questions which are already established by his own method. They classified that as a constructive replication. The second type of replication is Hendrick's application. He actually also divided the whole replication things in three types: strict replication, partial replication, and conceptual replication. So this is the one of the most famous replication type, and it is very recent. And most of the papers, while talking about the replication, they actually use this Hendrick's replication or Hendrick's classification. So the strict replication is to aim to replicate the original study as exactly as possible, considering the experimental design, experimental method, experimental variables. Like you have the same independent variable, you have the same dependent variable as exactly as possible. So it is actually highly matches the literal replication I already discussed. So this is the strict replication. So the second thing is the partial replication. That means you are bringing some changes in the main experimental method. So the changes can like, is it like a slight changes like addition or deletion, some of the independent or dependent variables, or slight changes in the experimental design to see that how you can replicate the previous study, or are you getting any new findings or not. So this is like the things like you are replicate the previous work, but you are slightly changing some experimental variables, you are adding some, or you are deleting some part from the experiment. This is the partial replication, which is quite similar from the Likens operational replication. So the third one is the conceptual replication. Here, the researchers come from a different method, but exploring the same research question or the same research findings that are established before by the original study. So using different method means you're investigating an idea which is already investigated by other people. They have a theory, they establish the findings. Now you have a different approach and you are trying to do the same thing, and you are uh, checking that whether this result is getting you, are you getting that result or not. So this is the conceptual replication. And if you think two classification I discussed, the inner meaning in both classifications are actually same. So replication can be strict, it can be partial, or it can be conceptual. So is there any questions on that, like based on the replication chronology or replication types? Uh, is there any questions on that?
I pointed out in a post that this kind of, with the way the XR device has changed so much, this kind of gives you more of a sense of what.
Yes, what kind of replication types it will be?
Yeah, strict replication is very hard.
Oh, okay, so I can move forward. So the replication studies in human-computer interaction. So I believe that this is actually highly related to our own research field, the human-computer interaction. So I explored like what actually going on in that particular research domain. So I found that there's a paper like named "Is Once Enough" on the extent and content of replication in human-computer interaction. So this paper published in the Chi conference and published in 2014, they actually explore the replication in human-computer interaction by considering all the full papers from 2008 to 2010 of a key conference of human-computer interactions and 3 highly ranked journals. I'll show you the results after the next slide. So at first, when they're trying to do the exploration of the replication, they actually first set some of the criteria. So they say that, okay, the experiment should be empirical. It should include the quantitative data. That means you should have some results. It's not like a qualitative results. And you should report an experiment. And there should some human-based study. So for example, like computational models, comparing algorithms, those are not actually considered in the eligible criteria. So because they are trying to find that the replication based on the empirical basis. So this is the criteria they set up at first, and then they based on the criteria they started exploring the replication research. So they provided this table there, and you can see that they considered some highly ranked human computer interaction conference, CHI, and the journal, also International Journal of Human Computer Studies. And from the paper, you can see that there are papers total like 891, and among that 429 is eligible. And so the question is, now they have a total papers. From the total papers, based on their criteria, they have the eligible papers. Then how they collect the replication papers from the eligible papers? There's the question. So they mentioned that when a study tried to find or confirm, expand, or generalize the earlier studies finding, they mentioned that as a replication. So based on that, they actually struck the replication studies from the, replication studies from the eligible studies. So at first they have the total papers, then they have the eligible papers, then they have the replication papers. So this is their results. So they found that there are some replication results, there are some multiple studies results, there are some number of comparison results. So the thing is, the replication results, they've divided that into 3 parts. So what actually the multiple studies result? So in your research field, whenever we found a paper, some research mentioned multiple studies like experiment 1, experiment 2, experiment 3, and sometimes use the language like, okay, the experiment 2 is the replication of experiment 1, but we are extending this thing. The experiment 3 is a replication of experiment 2. We're extending this thing. So they consider those kind of paper as a related experiments paper. Those paper are not the replication paper. And the paper, they found the number comparison. So they provided that, okay, we have this output. These people also have the output. They compare these 2 numbers, and they didn't count that as a replication. So based on their criteria and based on their replication criteria, they found their replication papers, strict replication, partial replication, and the conceptual replication. So if you look at this portion, like only on the replication portion, you can find that there are total 28 replication papers they found, which is 6.5% of the eligible papers and just 3.1% of the full sample. So the next question that the earlier findings confirm, like how many of them are successful, how many of them are unsuccessful. So they found that only from among the 28 replication papers, 14 papers perform a successful replication, and 3 papers fail to replicate, and 4 papers are undefined. So the next question, whose work is actually replicated? Is the replication work is done by the author of the original paper, or is the different people actually replicating the things? I mean, the different people or different lab. So they found that 22 studies replicate the work of other researchers. That's actually a great thing. Like someone has the original study and someone else actually replicated that study. So that criteria, they found 22 studies. That's quite a lot. And 2 studies actually replicate their own work. So that means that yeah, I'm the author, I published a work, and then I actually want to replicate my own work. So they found like there's a 2 studies like this. So they actually did a very interesting thing after their study. I mean, after the investigation, they contacted the paper authors of the 28 replication papers and asking their review, like, what do authors of replication think? They found that 13 reported while there were content replication, but their main goal was not replicate the original study. So the thing is, say after extending or after getting the data, they actually contacted the authors of the original papers and asking, what do you think about your work? And their 13 reported, okay, this is the replication, but their goal or publishing of things is not the replication. Their main goal was to find research additional topics or extend the original work, something like that. So what they actually did, so did the replication and then extend it, or did the replication and find some additional topics, but their main goal was not to replicate the original study. So cool thing is this is not the only paper who is talking about the replication studies in human computer interaction. Some previous paper, they're also talking about this replication things in the human computer interaction field. And in 2013, they have actually workshop on the replication research on the human computer interaction. So I found that, I mean, based on my knowledge, I can say that this is just in 2013. Maybe they don't have any other, they didn't continue it. Just in 2013, they have a workshop on that. So the second thing I want to talk about the replication studies in human factors research. So before moving to that, I want to say like any questions on the replication research in human computer interaction. And one thing I need to mention that in the Discord, you can see that I'm actually typing and answering the questions. This is not me. This is Dr. Swan.
I said that I was commenting as you.
Oh, okay. Yes. Any questions on that? All right. So next thing is replication studies in human factors research. So let's say that is there any replication studies going on in the human factors research? And one thing I need to mention that this is a multidisciplinary research, and so the result will be very interested. Let's see. So I also found a paper which actually investigating the replication research in human factors. So it published in also 2010 and in the Journal of Human Factors. And the method of their exploration is quite interesting, and which is different than the exploration method in the human computer interaction. So what actually they did? So in the method, they divided their whole considered articles into 2 parts. One is a parent article, and there is a child article. So what actually the parent article and the child article? So in the parent article, they considered an 1991 issue of Journal of Human Factors and they selected 8 articles from as a parent article. And in this child article, they considered the articles that cited the parent articles between 1991 to 2006, September 2006. Those are the child articles. So this is the two things, parent article and the child article, and the papers which is actually cited the parent article, they consider as a child article. So the next thing is they compared the child article against the parent article to determine whether it is replicated or not. Any non-empirical child article were omitted. So finding the parent article, child article, and then just comparing the two papers together and then saying that is it replicated or not, just simple like that. So, and then when they were found any non-empirical results, they just, or a non-empirical article, they just omitted. So the question is, are human factors studies replicated? So the answer is yes. There exist replications in the human factors research. So based on this paper, or based on their survey paper, they found a 30 replication papers. And if you look at this chart, you can see that there's an 8 parent article, and the y-axis showing the number of replications. You can see that article A actually replicated very frequently compared to article G and H. So, and they found this two type of replication, conceptual and the partial. So the next question is, how frequently are studies replicated? I mean, what is the mean value here among 0 to 10? So they found that the replication of the studies were replicated like a mean value of 3.75. And are the replications successful? They're the next question. So they found that among 30 replication papers, 28 were successful replication and just 2 was unsuccessful replication. So this also brings the issue of file drive problem, or you can say that as a publication biasness, because people try to celebrate only the successful work. And that's why when they have found a successful replication, they try to publish it. And maybe the unsuccessful replication were not mentioned or not reported. That's why the number of unsuccessful replication is small compared to the successful replication. So this is a very interesting thing. Any variation of the word replication, like replicate, replicated, was used in those papers. So they mentioned that 6 of the 30 replications included the word replication, and 24 publications, that is the 80%, that didn't include any language about the replication. That's the interesting thing. So those are the replication paper, but they are not mentioning any language about the replication, because the authors actually found that the replication, by reading both papers, comparing both papers, and by his own knowledge, he's deciding whether this paper is replicated papers or not. But in the article, they are not mentioning that, okay, this is a replication, we're doing the replication, or like something like that. So, and they're also saying that authors may not have known their research was a replication, or may not have considered their research to be a replication. So they are doing the research. So the authors of this survey paper, they actually determined that whether this is a replication paper or not. So the next question is a very interesting one. Who conducted the replication? Is the same author or the different author? So they found that there are 11 of the 30 replications were conducted by the original authors or co-authors, and the 19 was replicated by others. So this that being the question, like replication between the lab or replication among the lab members. So in the previous slide, I showed you that they found only the partial and conceptual replication. Here is the cool thing, that if you look at these two numbers, so when the replication is partial, that means you're bringing some slight changes in the replication study. The same author or same co-author, they are doing the replication more than the different author. But when the replication is conceptual, that means you are coming up with your own methods or own ideas, then you find that the replication is done more like with the different authors. So the partial replication and or the strict replication is more like the among the original authors and co-authors, but the conceptual replication was done by the different authors of the different lab. So the key point is here, replication exists and in the human factor research, and exact replications are rare. They only found the conceptual and the partial replications. And when you found, you not always found the replication paper as a mention that they're doing the replication. So it is the challenging thing that you need to identify the replication work. So any questions on that?
A little side discussion.
So the next thing is replication studies in augmented and virtual reality, and we can say that a mixed reality. So to our knowledge, we didn't find a research paper that systematically investigate the replication in AR/VR research domain. So therefore, we do not know the extent of the replication in mixed reality and the content of those replication. But we started working on that like a couple of months from ago. And so here in this tutorial, we will show you like our initial results and how the initial approach of our work and how we started. This is really, really initial. So we started a survey paper, just thinking like how we can start, like which paper we should consider. So we first started like at the conference thing, the conference paper, the two most famous conference in AR and VR, IEEE VR and ISMAR. And we're thinking of, okay, we can start from 2010 and let's see how far we can go. And only the peer-reviewed conference paper are considered. We are thinking at initially that no posters, workshops, papers will not be considered, only the conference paper, only the peer-reviewed conference paper as the initial way of thinking. Then, like the HCI paper, we selected or mentioned some eligible criteria. We mentioned that the paper should mention a mixed reality experiment and should be empirical and should have a quantitative data or the results that we have some statistical findings, and the paper should have a human basis study. So when we have the considered papers and then we have the eligible papers based on the eligible criteria, this part actually giving us the mixed reality based user status or mixed reality user based status. So after that, our goal is to find the replication papers from that set of the eligible papers or the set of mixed reality user based status. So according to the following the trend of the previous HCI papers, we just exploring that the replication papers must reference the original study and it should show an attempt to confirm, expand, or generalize the earlier studies finding. So that's the goal, that's the initial approach, like the theoretically how we can go. So the thing is, I will explain the search process of eligible papers to the replication papers, because finding and replication papers is very challenging, because one of the main reason is the papers do not mention the word replication in their paper. So we search the word at first to the replication in the paper's abstract, introduction, experimental task, and discussion, but it's very difficult to find a paper contains the replication word. Therefore, we used some other keywords like reproduce, follow-up study, earlier experiment, similar experiment, previous experiment to just extract the papers from the eligible papers. But that's not all. We need to further explore the eligible papers. We need to read the papers and need to figure out, okay, whether this paper is actually replication papers or not, by considering that is it actually mentioned in the original study, is it the data they are collecting, is it related to the original study, like not necessary to have the replication keyword. So we need to read the papers and confirm the results is a replication or not, and just comparing the results of the numbers with the original papers is not count as a replication, so it needs to prove experimentally. So this is actually the work we did. So let's see some initial results. like very initial results. So the question, why are mixed reality studies replicated? The answer, yes, there is a replication exists in augmented and virtual reality. So here's the table. So we initial goal was to from 2010 to how far we can go. So we started from 2010, but until this tutorial, we finished up to 2014. We finished the 5 years from 2010 to 2014. And we explore just the conference peer-reviewed papers. No journal paper is still considered. So if you look at this table, you can see that we found a total 9 replication papers, which is actually 3.59% of total paper. So far we have explored 251 papers published in ISMAR and IEEE VR. And from that paper, we found 78 eligible papers. And from 78 eligible papers, we found 9 replication papers, which is the 3.59% of total paper. And this is not surprising because the CHI, Human Computer Interaction Review paper, they found 3.1% of the full sample. So this is actually the encouraging thing that we are maybe in the right way. So still the work is ongoing. We are not cannot say that this is actually the right number. We need to explore more. We need to explore the journal. But let's break out this number in the per year. So in this graph, you can see 2 panels. The left panel is from ISMAR and the right panel is from IEEE VR. The green bar is showing the total paper published, and the middle bar is showing the eligible papers, and the right bar or the violet bar is showing the replication papers. Interesting fact is here. The interesting fact is ISMAR in the beginning, from 2000, 2011 to 2014, we didn't find a single replication papers. So what from my personal observation, I found that in that period, the people are actually investigating mainly on the tracking technologies, rendering technologies. Still, there's going research on that, but mostly focus on those things. Then, if you look at IEEE VR, in 2013, we don't have any replication papers, but each year we have at least one paper we found as a replication papers. However, if you look at this bar graph of the IEEE VR, in 2013 and 2014, you can see the total paper number is very low. So the reason is that in those time, in 2013 and 2014, IEEE VR accepted long papers directly goes to IEEE TVCG. Only the short papers considered as a conference paper, like 4-page short papers is considered as a conference paper. And if any paper published as a long papers, that directly goes to the IEEE TVCG. So in that moment, we don't have like a conference paper track. We had the conference paper track in IEEE VR, but that's mainly for the short papers. That's why this bar graph is low, because we didn't consider any journal publication yet.
All right, then. Talk about what you mean by eligible.
Oh, okay.
That's a question that's been asked.
So
Criteria for eligible.
yes, so let's bring here. So the criteria of the eligible is like the paper should a mixed reality based experiment. It should be
A human-based study. That's what the question was. Yes.
yes. This should be human-based study, and
Yes.
no computational models comparing the algorithms is not going to be considered, and we're just omitted that. Just human-based study, and in a word, we can say that is the mixed reality user-based studies. The eligible papers will give us, and from there we'll have the replication papers.
So the eligible doesn't mean it showed up with this keyword search method. That's a different thing.
Oh, eligible papers, no. Eligible papers is a different thing, because from the eligible papers, then the replication papers, we need to use this process like searching with the keyword, the replication, and then further exploring. In a word, actually, we need to actually carefully read the eligible papers until move to the replication papers, because very hard to identify the replication work. We are here. So the next thing is, let's see. So we have the augmented reality and VR. So I have just 9 replication papers, and among that, 4 published, 4 consider the experimental environment as augmented reality, and 5 consider the experimental environments as virtual reality. So in other words, in virtual reality, the technology could be VR HMD, or is it going to be virtual cave, or virtual treadmill, or simulator? Those all include in the virtual or VR thing. So I'm not actually showing the part like what kind of technology, VR technology they used, or what kind of AR technology they used. I'm just considering that AR and VR for now, like the replication paper goes to the AR is 4 and replication papers goes to the VR is 5. Next thing is based on the replication type. So the replication type means the strict replication, partial and conceptual. We're considering the Hendrix replication here. And unfortunately, we do not see any strict replication, that is 0. And the number partial replication is 3, and the high number is in conceptual replication, that is the 6. So this is the very, very initial results, and in future we'll extend our survey with more publication venues and years. Definitely, we'll consider IEEE TVCG and other venues to make it a more complete work. So this is the initial work. Good thing is that the way we are going is actually having some previous work support from the CAI or this HCI research, replication research. So this is the result of our own survey, replication survey paper that is currently in progress. So let's talk replication work from our lab, which you conducted, like how you actually want to perform a replication work. So in 2018, a paper published by Gavert, Mehra, and Dr. Swan, and the title is Effects of AR Display Context Switching and Focal Distance Switching on Human Performance. And if you look at this picture, you can see that this their experiment consider a very old Novate macrovision Novate display, a monocular display, and they consider a text-based visual search task. And in that paper, and so there could be a reason that this display is very old, and maybe the findings of the context switching and focal distance switching of AR display is only related to that particular display. Because unless you do the replication, you do not know how it works for the other display. So what we did, we considered a partial replication. We considered the same experimental task, same experimental procedure, but slightly modified the extent by extending the experimental variables, considered different AR display and more complex experimental design with an AR hyposcope. So same experiment, we are exploring the same research question, but the question is we are using 2 different AR display. So the reason is we want to make sure that the findings are generalized, the findings are is a general property in the AR VR research community. So that's why we performed this replication study, and the abstract is published in the last year at IEEE VR. We are also in the progress of the full paper, hopefully very soon. Cool thing is this graph. So we actually successfully replicated the experiment of Gavin, Mayer, and Swan, and we found a similar sort of impact of user performance and eye fatigue. So given many differences between these 2 displays, the hypotheses are consistent, and that actually broadly generalized to the optical see-through AR display. If you look at these two graphs is not from the same experiment. These 2 graphs are from 2 different experiments. The left graph is from the Gavard experiment with 24 participants, and the right graph is from the experiment using our AR haploscope with 24 participants. But if you look at the results, I'm not actually describing the graph. If you just visually with your eyes, if you look at the graph, you can see a significant effect, and that actually showing in both displays. So that means that the original study, we replicated the original study, we have the replication study, both finds the same thing. It given more confidence on the findings of the results. So that's the beauty of the replication studies. So that's the references which I consider in my presentation, and that's actually all from my side. And I think if you have any questions, please feel free to ask us.
Yes, so let's put this a little more in the middle.
I think I can move forward.
Well, don't move too far away. There, just tilt this so we're kind of both in the frame. So that's the end of the formal tutorial, but we're here and could ask a question, I think, if you're on the Zoom, you can just talk. I don't know.
And if you have a Discord,
Yeah, of course, you can type on Discord. Vicky is thanking us.
thank you.
Yes, thank you, Vicky. And wish we could just start talking now. That's always one of my favorite parts of the conference. Look forward to the next time that part can happen. Talking and getting a meal together after the tutorial.
Hopefully very soon.
Hopefully very soon, yeah. The conflict of interest and replication by different parties. So what do you mean by conflict of interest?
Yeah.
Would that mean that the replication is not successful? I'm not sure what that means. Let's see. I guess there could be a conflict if you try to replicate something and it can't be replicated. Okay, so I can tell we haven't left the internet because there's a kitten video. Ah, yes, if a result is not replicated. So yeah, this is, I can see this irritating somebody. If they have some result and they think it's great and it can't be replicated.
That doesn't mean that you already discussed that. That
Yeah,
if the replication study and the original study have different findings. So based on my understanding is that means that further exploration actually needed on that particular research.
so well, there is a large story here. You know, in part, the development of the institution of tenure was about letting people study whatever, you know, like, so that people could address research questions without their colleagues, you know, shutting them down or something like that. So just for an example, this doesn't have directly to do with replication, but it's a true story. So I did my PhD studies at Ohio State University. And at the time, there was a retired professor there named Chuck Suri, who I think is still alive and in his early 90s now. And he was one of the pioneers of computer art. He started making art with computers in the 1960s. And because of that, he founded the Computer Graphics Research Enterprise at Ohio State University in the 1960s. And therefore, Ohio State was an important early center of computer graphics research in the 70s and 80s, and continues to be a pretty significant place for computer graphics research and work in computer animation and stuff. So Chuck Suri was a professor of art in the 1950s, and he was also a well-known football player on the Ohio State University football team in the 30s and 40s. So that makes him a real campus hero. And even as an old man, he's like a big, tall, broad-shouldered guy. So it looks like a, you know, football player. And so he was a professor of art, and he started dabbling in using computers to make art because he would have lunch with a friend of his from mathematics. And at the time, the late 50s, Ohio State had one computer, you know, in a building. And he would be like, well, what do you use that thing for? And, you know, just talking about it. He told me that it was a very good thing that he had tenure because every one of his colleagues felt like he was totally wasting his time trying to make art with this computer, you know, and at that time, you know, computers did not have color monitors.
Mhm.
They didn't have monitors at all. You would write your code on punch cards. And this guy who helped found a whole field of research that our field is kind of, you know, based on partially, he made use of tenure to be able to pursue that. So it's not directly related to the question, but it's related to the larger issue of, you know, the power of curiosity-based scholarship. And in an ideal world, that's something that the institution of tenure protects and facilitates. Okay, sure. Sure. Yeah, I can see the Zoom. We have 3 monitors here. I can see the Zoom on one of the monitors.
Hi, thank you both so much for the great talk. I have a question about an earlier point about effect sizes and the fact that if I use the data that I have from my study, an example study, the effect size is similar to p-values. Am I correct in that point?
The p-value is a measure of the strength of the effect in an experiment.
So the effect size both of them mean the same thing. Is that correct? The effect size and the p-value from the results of the same study.
I'm going to unshare the screen so I can see you better. How do I do that?
Oh, okay. So,
Oh, down here.
just up here.
Stop. How do I stop? Pause share.
Oh.
Stop share. There we go. Okay, now it's easier to see everybody.
Okay.
So,
go ahead.
I'm sorry, ask that again. I didn't.
Sorry, this is a part that I think I maybe have misunderstood. So I think earlier in the talk you mentioned that effect sizes, we should calculate effect sizes based on previous research, and that is not something we have, for instance, in XR. So calculating effect sizes from the results of a study that I just did is very similar to the p-values that I have. Have I understood this point correctly?
Yeah, so the p-value, if you calculate the effect size, so one measure of the effect size is just the mean of what you measured. So in other words, you can report the effect size in the units in which you measured.
Yep.
So in the experiment I talked about, we measured the total time it took for people to navigate through some environment. And so that was measured in seconds. So we can report an effect size in that case in seconds of time. But in terms of power, a unit like that is only meaningful in the context of the variability found in the experiment. And so the more useful measures of effect size, which allow you to do all of those calculations, are normalized somehow according to the standard deviation of the experiment. And so the p-value is actually one such measure. It's like a normalized measure of the effect size of an experiment, and you can use it to turn the effect size into several different statistics, and I'm not a total expert on what all these statistics mean, but the statistic that was used in the reproducibility project was R, so the coefficient, a correlation coefficient. So I would have to do more scholarship myself to totally understand, you know, that measure of an effect size. But by turning everything into a correlation, that paper was able to then, you know, quantitatively examine effect sizes. So if you have a previous experiment you could use this measure of effect size, this correlation coefficient, and from that, you could recruit enough participants to know that you're going to be able to find with, say, 80% probability, you're going to be able to avoid a type 2 error, which would mean that if there was a true effect and you are replicating that effect, you know, you would have an 80% chance of finding it if it's there. But what you can't do is run an experiment and then use the measure of the effect size from your own experiment to validate whether you did that for your own experiment.
Because for instance, with some papers, I get reviewers' feedback. We already have the p-values. I understand that there should be like a correct procedure of reporting the results. So that aside, sometimes reviewer feedback is to also report the effect size of the same study, of this based on the same results.
Yeah,
because I
I've
don't
gotten
have a
that.
previous research. So
Yeah, I've gotten that same comment, and I've replied that the p-value is such a measure, and then I've given this the page number in my stats book where it talks about all this. So it
it's
is
not
useful to give the
necessarily
effect size in your paper in the units in which you measure. I mean, that's always useful too. But
Thank
the
you so much.
p-value is a measure of effect size.
Thank you
So
so
it's
much.
also
I think I
common to
understand better now.
like there's this partial eta squared that SPSS gives you,
Yeah.
but that varies with the p-value. So it's not that it's totally useless. It's just it's not necessary to report it. It's not completely necessary.
And if
I
I
mean,
can
if you
ask,
look at the equation that calculates the eta squared, if you've done an F test, it's calculated from the p-value and the F value and the degrees of freedom and stuff. So it's already, you know, it's calculated.
a very hopefully quick question is that, for instance, I've seen in papers that when they have like a lot of conditions, they do some sort of correction, such as Bonferroni correction, to make sure that they're actually looking at meaningful p-values. And I've seen that sometimes they refer to their own effect sizes from the same results to say that we don't include the significant p-values that have a small effect size and only focus on larger effect sizes. Again, effect size is calculated from the same p-value. So this suffers from the same issue, right? Or is it a different thing?
Well, another thing that happens statistically, so some of my own papers have similar language, is that you can find significant effects. You can find significant values for effects that are so small that they have no meaning in the context of your experiment. So for example, we've done these studies where we've looked at the perceptual positioning of virtual objects. And if you're positioning an object that's say 2 centimeters across, and you're positioning it on a grid of maybe 30 centimeters, and you find some significant effect that's talking about a fraction of a millimeter, that's such a small effect that even if it is significant, it has no meaning based on the larger experiment. And so the paper may have been making that kind of argument, that there's a certain effect size that's going to be meaningful in this experiment. And if we find something that's smaller than that, even if it is truly significant and a real effect, it's too small to matter. So it depends on how that's stated in the paper. But I have that same language in some papers that I've written. And statistics, you know, the textbooks that I've read talk about considering effect sizes as well, that's you know, considered a good experimental design and analysis principle.
Thank you so much.
But considering is different than claiming an effect size from within your own experiment.
Yeah.
as a justification for the number of participants that you recruited. Let's see. Effect size, Tabitha's, effect sizes are needed for meta-analysis. The data in the paper, the effect size cannot always be calculated directly from the p-values. So I think Tabitha is making an important point as well. So I don't totally follow, but it's more complicated than what I just said. It's not that the p-value contains all of the information, but it contains a lot of information anyway. Oh, okay. And then you need the Zoom stream for the next thing, don't you? Yeah, yeah. Sounds right. Okay, so I guess the Discord will stay up, and I hope I see many of you at some of the social events that are also part of this. Of course, I wish we were physically together, maybe next year in New Zealand. Wouldn't that be fun? And you know, and I hope to see you all, and thanks for attending. We will now give up the Zoom stream back to the conference.
Thank you. Bye.
Thank you.